Hello everyone and welcome to the last session of this series solution of linear differential equation. In our curriculum we have taken the syllabus up to Legendre's differential equation, series solution of Legendre's differential equation. So let us solve the Legendre's differential equation and we conclude this unit. So here Legendre's differential equation is, what is the Legendre's differential equation? First see the definition. The differential equation of the form 1 minus x square d2y by dx square minus 2x dy by dx plus n into n plus 1 y is equal to 0. 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 y is equal to 0. It is called Legendre's differential equation of order n into n plus 1 we required. Now check that whether your point is regular singular point or ordinary point. For that, p0 of x. What is our p0 of x here? 1 minus x square. If I put x equal to 0, then I get here p0 of 0 is 1, not equal to 0. So our x equal to 0 is our ordinary point. And we know the method to solve ordinary point. We take y is equal to ak x raised to k. Series ak x raised to k varies from 0 to infinity. Have you remember? Dy by dx is k equal to 1 to infinity k ak x raised to k minus 1. D square y by dx square it is k equal to 2 to infinity k minus 1 ak x raised to k minus 2. Right? Do it. Put these values in your given equation. In Legendre's equation. Solve it completely. Yes. And find different values of a2, a3, a4 in terms of a0 and a1. Do it. The same procedure we use and we get solution of Legendre's equation. So here 1 minus x square series k equal to 2 to infinity k minus 1 ak x raised to k minus 2 minus 2x k equal to 1 to infinity k ak x raised to k minus 1 plus n into n plus 1 k equal to 0 to infinity ak x raised to k equal to 0. What we did, have you remember? We just make its power m. So m is equal to k minus 2 we substitute. Here also we substitute k minus 1 is equal to m. But before that, multiply this 1 inside, then x square inside, x inside and simplify the term. So the simplification term is k equal to 2 to infinity k minus 1 ak x raised to k minus 2 because 1 we have multiplied. Now multiply x square. So this x square and minus 2 goes away. I get ak x raised to k. Then here multiply x inside. So here again I get k ak x raised to k. And last term as it is n plus 1 ak x raised to k series k equal to 0 to infinity. Now here in this 3 term I can directly take k equal to m, but in the first term I have to take k minus 2 is equal to m. K minus 2 is equal to m. I hope you remember. Put k minus 2 is equal to m. So m is equal to, k is equal to m plus 2. And as my k starts from 2, my m starts from 0. So that concept we are going to use here. Use that concept and write down the series in terms of m now. So m equal to 0 to infinity, m plus 2, m plus 1, am plus 2, x raised to m minus m equal to 2 to infinity, m minus 1, am x raised to m. I know that you have understood the concept, that's why I am just reading it instead of writing because I have to complete within a time this equation. So here minus 2, m equal to 1 to infinity, am x raised to m plus n into n plus 1, m equal to 0 to infinity, am x raised to m equal to 0. Okay, now here if you see the terms series highest here it starts from m equal to 2. So from the remaining series we can take few terms outside so that my series gets started from 2. Just like here m equal to 0. Substitute here m equal to 0, what I get? 2 into 1 here a2. Right? So 2 into 1 a2 plus, now put m equal to 1. Yes, 1 plus 2 3 into 2 a3 x. Got it? Plus now m equal to 2 to infinity. Write down in series m equal to 2 to infinity, m plus 2 m plus 1 am plus 2 x raised to m. So first term over minus Second term already starts from m equal to 2, keep as it is. Minus m equal to 2 to infinity m minus 1 am x raised to m. Correct. Now third term. In the third term, m starts from 1. So take that one term outside. What is that? Put m equal to 1. 1a1 and minus 2 there. So minus 2a1 and x raised to 1. Okay. And now m starts from 2 to infinity. So here minus 2 m equal to 2 to infinity m x raised to m. Right. And last term, here I have to start from m equal to 2. So 2 terms I have to take outside. Which are that? M equal to 0, a0. So n plus 1 a0. n plus 1 a0 plus. Put n equal to 1. n plus 1 a1 x. Right? Plus n plus 1 series m equal to 2 to infinity am x raised to m equal to 0. Now take the coefficient terms and equate to 0. Which are the which are the constant term here? 2a2, see 2a2, then here n plus 1 a0 equal to 0. So I get a2 is equal to minus of n plus 1 upon 2 a0. Getting the value of a2. Now find a value of a3. 6a3, here 6a3 minus 2a1 plus n into n plus 1 a1 is equal to 0. 6a3 minus 2a1 n into n plus 1 a1 is equal to 0. Right? Now simplify this. If you simplify, what will you get? Tell me. 6a3 plus, if I simplify, I get n square plus n minus 2a1 is equal to 0. So from this you will get the value in terms of a3. So a3 is equal to minus a1 n square plus n minus 2 upon 6. Find the factors of this term. It is n minus 1 and n plus 2. So value of a3 is equal to minus n minus 1 n plus 2 upon 6 means 3 factorial a1. You may write 6 or 3 factorial, doesn't matter. Similarly, you can find a4, a5 and so on. For that, we just write down our general term. We know that in ordinary point we take the coefficient of x raised to m and write down the general term. So write down the general term, equate the coefficient of x raised to m equal to 0, you will get m plus 2, m plus 1, am plus 2 minus m minus 1 am minus 2m am plus n plus 1 am is equal to 0. Now I can make it simple. For that, transfer this am term to RHS. Now I will show you this calculation, how to do it. Right? Here. Now see carefully this calculation. Here, am plus 2 is equal to, from this term take am outside and what remains tell me. And all these terms we are going to transfer into RHS. So what I get, tell me. Here minus term becomes positive. So m minus 1, right, plus 2m, correct, plus minus n plus 1 am upon m plus 2 into m plus 1. What I did, I just transfer all this term to RHS so that minus become plus there and plus becomes minus. Understood? Now I simplify it. m minus 1, here multiply inside, m square minus m plus 2m minus n square minus n upon m plus 2 m plus 1 am. Correct? Now here m square minus m and 2m, it becomes plus m. Now m square and minus n square we can take in one bracket. So here m square minus n square in one bracket, right, plus what is the remaining term? M minus n, this one, m minus m, correct, these two term. From this I get m and here minus n upon m plus 2 m plus 1 am. Understood? Now m square minus n square I can write m minus n into m plus n plus m minus n as it is upon m plus 2 m plus 1 am. Now you can take m minus n common. What I get? M minus n into m plus n plus 1 upon m plus 2 m plus 1 am. Understood this step? Right? So we did write this step here in the calculation. Am plus 2 is equal to m minus n plus 1 upon m plus 2 m plus 1 am. Correct? Now put all these values in your y. Because we have now general values, we can put n equal to 2, n equal to 3, n equal to 4, and we can find so many values. So similar way, find a4, a5, a6, whatever number of values you have to find and put that values in y. So our y becomes a0 plus a1x. Now here a2x square, that I can write minus n plus 1 upon 2 factorial a0x square minus then a3 you can find minus n minus 1 n plus 2 upon 3 factorial x cube a1, and similarly a4 a5 you can write. And finally you can see there are only two terms present, a0 and a1 coefficients present, right? So take a0 outside and a1 outside and write down two terms for the series. So here a0 in bracket 1 minus n plus 1 upon 2 factorial x square plus n minus 2 n plus 1 n plus 3 upon 4 factorial x raised to 4 plus so on, and the coefficient of a1 is x minus n minus 1 n plus 2 upon 3 factorial x cube plus so on. Means even and odd powers get separated, right? So my final answer is y is equal to c1 y1 plus c2 y2, means this a0 I can call it c1, remaining term is y1, and a1 I call it c2, remaining term is y2. In further calculations, we can write this solution in terms of Pn of x and Qn of x, and we can call it as Legendre's polynomial, but that is not the part included in our syllabus, so we stop up to this point and conclude this unit. For practice purpose, you may solve examples of ordinary point, then examples of Bessel functions I have given, then examples on singular point. So many examples are there. Solve all examples, and if you found some difficulty, then you approach us to me, right? And if you like it, then comment in like section or comment section. Thank you for watching.